Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on January 8th, 2026, just yesterday. It identifies a critical flaw called reward signal collapse in current multi-reward reinforcement learning and proposes a solution that boosts math reasoning accuracy by up to 6.3% while strictly following constraints. The paper is titled GDPO, Group Reward Decoupled Normalization Policy Optimization for Multi-Reward RL Optimization. And, as we'll see later, the way this method balances conflicting goals without losing training stability is really impressive. And for those interested in the implementation, the authors have shared their code on GitHub. So Figure 1 breaks down the core innovation and its immediate impact. On the left, Panel A contrasts the standard approach with the new method. In standard GRPO, shown in the red box, distinct rewards are simply summed up before being normalized, which often causes the unique signal from each goal to collapse. By comparison, GDPO, outlined in the green box, normalizes each reward individually first. This decoupling preserves the specific feedback from every objective. Moving to the right in Panel B, the performance curves confirm the benefit. The green lines for GDPO rise faster and higher than the gray lines, showing that the model learns both proper formatting and correctness more reliably. Alright, Figure 2 illustrates exactly how that signal collapse happens with a concrete example. On the left side, using the standard GRPO method, we see that different reward combinations often map to identical advantage values. Because the rewards are summed before normalization, distinct outcomes, like a 0 and 1 pair versus a 0 and 2 pair, get compressed into just two advantage groups. In contrast, the right side shows how GDPO normalizes separately. This approach preserves the granularity, distinguishing three unique groups of advantages, which provides the model with much clearer feedback. Well, Figure 2 just showed a single case of signal collapse. Now, Figure 3 quantifies how this problem scales up across the board. On the left, we track what happens as the number of rollouts increases. The steep green line for GDPO shows it generates far more distinct advantage groups than the gray and blue lines representing GRPO variants. The contrast is even starker in the right chart, which adds more rewards. Here, GDPO maintains a massive number of distinct signal values, whereas the standard methods flatten out, confirming they lose critical feedback resolution. So, with the signal collapse issue clarified in Figure 3, Table 1 demonstrates the real-world impact on tool calling. Using QWEN 2.5 instruct models, the table compares standard GRPO against the new method. In the 1.5 billion parameter section, GDPO leads, boosting average accuracy to nearly 33% compared to roughly 30% for GRPO. Crucially, the final column shows this doesn't cost structure. The model achieves over 80% format correctness, a 4% jump. These gains repeat in the 3 billion parameter section below, confirming the method's robustness. Okay, while Table 1 focused on tool calling, Figure 5 examines training dynamics for mathematical reasoning. This figure tracks three metrics over 500 steps to illustrate stability. On the left, the correctness reward initially drops for both methods as they prioritize length, but notice how the green GDPO line recovers and climbs, whereas the gray GRPO line degrades late in training. The middle panel confirms that both methods maximize the easier length reward quickly. However, the right panel reveals a critical failure. While GDPO keeps response lengths controlled, the gray line spikes dramatically at the end, showing that the standard method eventually forgets constraints. Alright, following the training dynamics, Table 3 lists the final performance across 5 math benchmarks. Focusing on the DeepSeek R1 1.5 billion model on the left, the aim row highlights the core trade-off. The baseline model achieves about 30% accuracy, but fails the length constraint over 90% of the time. Standard GRPO reduces those violations, but drags accuracy down to 23%. In contrast, GDPO restores accuracy to nearly 30%, while cutting violations even further to just 6.5%, a pattern that holds true for the larger models on the right. Wrapping up, two takeaways stand out. Standard methods lose critical signal when summing rewards, and decoupling normalization restores that precision. This allows GDPO to balance accuracy and strict constraints without trading one for the other, offering a stable foundation for aligning models with complex human needs. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.